How about the distance between two straight lines? There are actually three possibilities when you have two straight lines. The two straight lines could be exactly the same. Then the distance would be 0, of course. But this case does not really make sense for this type of exercise, so usually your teacher or professor should note in the exercise you can assume that both straight lines are not the same, or are not, how to say, equivalent. Or maybe you can ask to make sure that, since, you can prove it in an exam, but it takes time, or you can check whether they're the same or not. But it doesn't really make sense for this type of exercise. So we assume the two straight lines are either parallel or they are skew, like this, right? So they don't touch each other, like this. And also in this case, of course, it wouldn't make sense a lot to determine the distance, since also distance, the smallest distance at least would be 0. And so they are skew like this, and you can calculate a distance, smallest distance, and they could also be parallel, then it's a little bit easier to calculate. So these are the two cases I will show you in the following video. And I think this is a little bit more complicated, but you just need practice. When you practice a lot, then it's also not that difficult, since it's always the same procedure. Check whether it's parallel, both are parallel or skew, and then you can apply the procedure. So I will show you in the following video. How to calculate the distance between two straight lines. This is actually a little bit tricky, but once you've understood the procedure, it's actually also, I would say, quite easy again. But so let's first have a look at the principle. So when we have two straight lines, they can either be parallel, or they could also be the same. But that's not very interesting. Then the distance would just be 0. But we assume we have either parallel straight lines or we have skew straight lines, like this. And for what you need this calculation is, for example, if you have two aircrafts in the sky and you want to know how close do they come, or do they have maybe intersection point, but in this case we don't have an intersection point. We want to really calculate a distance. So the planes are like this, skew in the air, and we want to know how close do they get to each other. And you can also apply this, for example, for submarines in the ocean or cables in the ground. You just have two straight lines and you want to know how close do they get. And in one case they're parallel, so they always have the same distance, and in the other case they're skew and around in the area, in the sky or in the water or in the ground, in the ground. So we just need it a little bit on paper. So how does it work? First case, we say our straight lines are parallel. Okay, when our straight lines are parallel, how does it work? I'm going to show you the principle. So this is our plane. This is first straight line. First straight line goes through here. And so the thing is, we need an auxiliary plane, which is this one. And there you see we have an intersection point, and this intersection point we assume is our, how is it called, our support vector of the straight line. I'm going to show you later what it is exactly. And the principle is, now we we calculate an intersection point with the second straight line, like this. So we intersect the plane with the other straight line, and then we get another intersection point here. And then we calculate the connecting vector between both. Maybe I just remove the straight lines. Then you see two holes. Those are our intersection points. And then what we do is we calculate the connecting vector between those two intersection points, and then we just take the amount of it, and then we know the distance. It's actually not too difficult. Maybe you can keep it in mind with this demonstration. I'm going to show you on paper now how it works. And the principle, as I just said, is we need an auxiliary plane, which is P in this case. Maybe I'm going also to show you the example parallel to our parallel example. So we just have two straight lines. One is called G, which is -9, 1, 4. This is the support vector. And the other one, this is our directional vector, which is -5, 0, 0, and U. Okay, and we have another one which is called V, element R. And the V is in the other straight line, which is called H. 2, -3, and 1, plus V, 0, 10, 0. Two straight lines, support vector, directional vector, and so maybe I also write it here. So we have three components, and I call this the U vector, which has like U1, U2, U3, and same with V, V1, V2, V3. But at this moment we just need U. This I call vector A. So this is the support vector of our first straight line. And then, what else? We need the support vector of the second straight line we need. And we call this, I would say, P. It doesn't really matter, we can also call it B, or let's say P. Or point P, maybe. It's the same, but we need it later. This is which the support vector which you need in the third step. So in the first step we just need the first straight line, and then we calculate the intersection with the second straight line. And so just keep in mind this example how it works. So now I'm going to show you the procedure. We have our plane, which is U1. So you remember the U, right? I just showed you. This is the U vector. So U1 x1 plus U2 x2 plus U3 x3 equals A. You remember the A, which I used here. That's our support vector from the straight line 1. We multiply the support vector from straight line 1 with the directional vector of our straight line 1. And note this representation, this is called the coordinate representation of our plane. Then, second step, we need the intersection of P. So now I realize maybe it's not good also to call this point P, so we call it differently. I'm thinking of a name. So first step 2, intersection of P with the second straight line. And then we call this point S, and then we can calculate in the third step we need the point of the first straight line, so we have to keep it to compare apples to apples, right? So this is S, this is our intersection point, and we say A is the vector of point A, right? And this is point A, this is our support, this is our support vector of the first straight line, and S is the intersection of P with the second straight line. So what are we going to do is, we say D, that's the distance, is the amount now of the intersection point with the second straight line, which is S, and the support vector of the first straight line, which we said is A. Then we calculate the amount, and then we have the distance. So don't be confused by my notation. So A, as I said, is the point, is the support, or this is the point where the first straight line goes through, right? This is A. And S is our intersection of the plane P with the second straight line, which is here, which is H in our case. And remember, so first point, one point is the support vector of the first straight line, and the other point is the intersection point of the auxiliary plane with the second straight line. So just maybe you can watch the video several times so that you can understand it, and when you have it really in your mind, then you're ready, then you can practice, and then you can take the exam. And I don't think it's really difficult, but you just have to be aware of this principle with the auxiliary plane, and then it's not too difficult. You can also take this with you maybe in the exam, or maybe not, but you should memorize the principle, and then it's not too difficult. So, but in our case, so these actually, that I can tell you maybe before we start, both directional vectors, as you may see, are linear independent. So how can I see that? It's very easy in this case because we have two components which are zero, so I just have to look at the first component and I already see, okay, this both should be independent because here's a zero, here's a number, and also I can easily see that one vector is not a multiple of the other vector, right? So when I would multiply this vector with anything, any number in the world, I would never end up with this vector. And same other way around. So both directional vectors in this case are linear independent. And therefore, when they're linear independent, what did I want to say? Yes, and when they are linear independent, then they cannot be parallel, right? So we cannot use the procedure I just explained. But we can use another procedure, which is point B, which is called skew. And skew means, as I said earlier, we have two straight lines, and those two straight lines are not parallel, as in the first case, but they're skew. So something like this. You see, okay, they don't have an intersection point, they're not parallel, they're just some strange, something like this in the sky or in the ground or in the water, you know, but not parallel, and they don't have an intersection point. So, how does it work? This case is actually quite easy. You don't have to think a lot. You just need a formula. And the formula is the following. So we have D is the distance between those two straight lines, G and H. The formula is A minus B, and those two are the support vectors of the straight lines. A is the support vector of G, for example, and B is the support vector of H. Remember, G and H are our straight lines in the example. Then we multiply the result with a vector called n. N is the normal vector. I'm going to show you how to calculate it, and also the principle behind the normal vector. But in this video, I don't really want to explain it in that detail, but I just want to refresh what is n and divide it by the amount of n. So n, in principle, for what you need n for is usually if you have a plane and you want to describe the plane. How can you do that? You can describe it by how many points? Maybe 3 points. Or you could describe it by a vector and 1 point. So the thing that works is we have a vector somewhere in the area, and we say, okay, we just need 1 point here, then we can describe a plane. Because, like for example, the assumption is always that the vector is normal, is 90 degrees to the plane. Then I can say, okay, the plane is a variable on this vector. I can move it like this, but it should be 90 degrees. And as soon as I tell about 1 point, it is fixed. And the plane is completely expressed and really defined. In, so it cannot be moved anymore, or like this, it is defined. So I need one vector, which is called a normal vector, which is 90 degrees to the plane, and 1 point. And that's what you need the normal vector usually for. So normal vector definition I can show you, because we need to calculate it. For the formula A and B are already, we just have to read, which might also be a problem sometimes in exams, but we have it given, so we just assume we can transfer it to our formula and then calculate it. We don't make any mistakes. But n, we need to calculate. So there are two procedures. You can calculate the cross product, or you can calculate it like this. I tend to calculate it like this. This is maybe not the shortest way, but I just like it. I never make mistakes. I never make mistakes with it, so that's how I do it. We have two directional vectors. You remember? U and V. So this I call U. This directional vector I call V, and I can say a normal vector should be 90 degrees to both those vectors. So we have two straight lines in the area. So a normal vector, what does it do? Normal vector is 90 degrees to both. For example, like this. And the way to calculate it works the following. We just have to, like I do it with the definition of linear independence, and I say when I multiply the directional vector of one straight line with the normal vector, it should result in 0. That's the definition, like of 90 degrees between two vectors. And I also say it has to be a 90 degrees to the other vector, to the other directional vector, which is called V. So that's what I'm going to calculate. And the way it works is just you take U1 N1 plus U2 N2 plus U3 N3 equals 0. And so on. So, but I just calculated with the real number, so you keep in mind our example. I showed here U and V, and so I have minus 5 and 1 plus 0 and 2 plus 0 and 3 equals 0. For V I have 0 and 1 plus 10 and 2 plus 0 and 3 equals 0. Then I can build a matrix, which is minus 5, 0, 0, 0, 0, 10, 0, 0. And I just like this definition because of the matrix, actually. And then I can calculate first row by minus 5, second row by 10. I end up with 1, 0, 0, 0, 0, 1, 0, 0. Then I see, okay, x or n1 has always to be 0, n2 always 0, n3 not defined, so I can choose. So my normal vector is, and I call it nt, is 0, 0, t, t element r. So that's a very general normal vector, and I'm going to choose what I'm going to choose, I think 5. Yes, I choose 5. So we say n5 is 0, 0, 5, and that's a perfect normal vector to our two directional vectors from the example. So now we can just calculate it. Actually, we have everything. We have all the information we need. So we have d, g, h. Our distance is now 1 minus b is minus 9, 1, 4 minus 2 minus 3, 1. So if you want to, where I'm getting those numbers, just a and b, those are our two support vectors, and I subtract them. And brackets, so it looks a little bit ugly in this case, but I'm going to read it to you so you understand. So minus 9, 1, 4, 2, minus 3, and 1. Subtract both support vectors, multiply with the normal vector, and take the amount, divide by the amount of our normal vector. So we end up with minus 9 minus 2 is minus 11. 1 plus 3, 4. 4 minus 1, 3. Then we multiply with our normal vector. divide by the amount of our normal vector, and we end up with, when we multiply, we end up with 15 and divide by 5. And I already calculated the amount now, because the amount, when I multiply this, we end up with 0, 0, 15. And the amount, if you only have one element, like one component, and the other ones are 0, then it is just the amount is just this one component. Why? When I take the amount, I could show you, for example, when I take the amount of n5, for example, would be defined like this, amount of 0, 0, 5. You calculate like this, 0 squared plus 0 squared plus 5 squared and square root, right? But 0 and 0 squared is both 0, 5 squared is 25, square root of 25 is 5, right? So that's what I did here in my head, and I end up with 15 and 5, and 15 in the numerator, 5 in the denominator, and then I just have to cancel out, and 3, 1 is 3. So we just calculated very quickly the distance between two straight lines which are skew. Very, very easy. Just apply the formula. You should know the formula by heart though, but otherwise it's very easy. You just put in your information. One thing, of course, you need to calculate the normal vector. If you prefer the cross product, then do it. If you like this definition, I just like it because of the metrics, because I like the definition of the linear independency or linear dependency, how it works with the 90 degrees, and I just prefer it, and so I use it like this, and I don't make any mistakes usually when I calculate like this. So not too difficult, just you have to distinguish between two cases, parallel and skew. Parallel, you can visualize it. You have an auxiliary plane, a plane, and you calculate the intersection point between your auxiliary plane and the second straight line, and then you can calculate the connecting vector between the intersection point and the support point, the support vector of your first straight line, then take the amount, then you have the distance. When your two straight lines are skew, then you use the formula. Just put in both your support vectors, calculate the normal vector. When you have the normal vector, you can put it in your formula, just multiply, division, and you end up with the distance. So it's not too difficult, I would say, but a little bit tricky, and you should practice it, and practice it a lot maybe, so that you're also fast, you don't make any mistakes, and then you can be sure that it works in the exam, or whenever you need it. Thanks for watching. Practice makes perfect. Further exercises with solutions you can find on my website, which is www.worksheets.com.